In the charge transfer regime, a low-energy model for the bilayer nickelate Li3 Ni207 is proposed, where doped holes enter the oxygen p orbitals, contrasting with previous models based on the Ni-dx2Y2 and dz2 orbitals. The parent nickel state is in the 3d8 configuration with a Spinoni moment, which is only screened down to spin-half by doped holes, unlike the Zhang-Rice singlet in cuprates. This single-hole state is dubbed the Zhang-Rice spin-half, and an effective model is built, including 3 Spinoni states, D8, and 2 Zhang-Rice spin-half states, D8L. At moderate pressure around 20 gigapascals, the dominant oxygen orbital is an in-plane Wannier orbital with the same lattice symmetry as the dx2y2 orbital, reducing the model to the bilayer type 2 TJ model previously proposed in the Mott-Hubbard regime. Density matrix renormalization group, DMRG, simulation reveals a pairing dome with the optimal hole doping level at x equals 0.40.5, distinct from the holodopt cuprate where optimal doping occurs around x equals 0.19. Further increasing pressure initially raises the critical temperature, Tc, until reaching an optimal pressure beyond which the pz orbital of oxygen becomes favorable and superconductivity is diminished. This shift from in-plane p orbital to pz orbital may elucidate the experimentally observed superconducting dome with varying pressure. A trilayer version of the Type 2 TJ model is suggested as the minimal model for pressured Li4 Ni3010, distinct from the models in the Mott-Hubbard regime. The valence of the nickel, Ni, atom in the bilayer nickelate Li3 Ni207 is in the 3d8x configuration, according to density functional theory, DFT. A bilayer type IITJ model is demonstrated to be the minimal model, including the Spinoni Ni2 plus state, 3d8, and spin-half Ni3 plus state, 3d7, at each site. This model hosts unique physics, such as a dome of pairing gap around x approximately equals 0.5 due to doping-induced Bardeen-Cooper-Schrieffer (BCS) to Bose-Einstein condensate (Beck) crossover. The research paper explores the behavior of doped holes in bilayer nickelates, with a particular focus on the Zhang-Rice spin-half state. Unlike cuprates, where the doped hole reduces the Spinoni moment to spin-half, the authors demonstrate that the doped hole in bilayer nickelates enters the in-plane oxygen orbital and forms a net spin-half moment together with the Ni-Spinoni moment at moderate pressure. This whole state is referred to as the Zhang-Rice spin-half. The authors employ a type IITJ model, which is identified as the minimal model in the charge transfer regime of the doped bilayer nickelates. They reveal that the oxygen pz orbital, located between the two layers, can only facilitate a very small interlayer hopping T-up tag due to symmetry. Density matrix renormalization group, DMRG, simulations show that the pairing gradually decreases with T-up tag but remains robust. However, if the interlayer hopping is further increased beyond an optimal value, the doped hole shifts from the intralayer px, py oxygen orbital to the interlayer pz oxygen, and the pairing is suppressed. The authors consider a charge transfer model on a bilayer square lattice, including 3 orbitals of oxygen and 2 Eg orbitals of nickel. The Hamiltonian is composed of several terms, including the on-site energy, intraorbital and interorbital on-site repulsion, Hund coupling, and nearest neighbor hopping between dp orbitals. The authors then focus on the Zhang-Rice spin-half state, where the doped hole enters the oxygen orbitals and interacts with the localized Spinoni moments from the Ni2 plus state through a Kondo coupling. In the strong coupling limit, the hole enters the oxygen orbitals and forms a Zhang-Rice spin-half state. The lattice structure and p, d orbitals of the bilayer nickelates Li3 Ni207 are illustrated in Figure 1. The symmetry analysis of the orbitals is provided in the supplemental material. In bilayer nickelates, a theoretical model is presented for the Zhang-Rice spin-half state, a phenomenon observed in the charge transfer regime. This model is based on a multi-orbital Hubbard model, incorporating the dorbitals of Ni atoms and orbitals of oxygen atoms. The Kondo couplings, Jk, A and Jk, Z, describe the interactions between these orbitals. Density functional theory calculations yield hopping parameters TdP, 1, TdP, 2, and TdP, Z, used to estimate the Kondo couplings. The results indicate a strong anisotropy in the Kondo interactions, with Jk Z being approximately 1/4 of Jk 1. The ground state energies resulting from the Kondo interactions are calculated, denoted as EAG and EZG for the in-plane Pa orbital and the PZ orbital, respectively. The results show that the P1 orbital is favored over the PZ orbital due to the stronger Kondo coupling. The Zhang-Rice spin-half state is a spin-half state formed by the doped hole in the P1 orbital and the original spinoni moment from the Ni2+ ion. The wave function of this state, given by equation 4, depends on the parameter r equals Jk 1, Jh. Figure 2 illustrates the spin contributions from the P1, D1, and D2 orbitals, demonstrating that in the limit of Jh much less than Jk 1, the Zhang-Rice spin-half state is a simple product state of the Zhang-Rice singlet made by D1, P1, and the decoupled D2 orbital. However, for general values of Jh, the three orbitals are highly entangled and should be considered together. The development of a type IITJ model for the charge transfer regime in bilayer nicolates is discussed, focusing on the electron picture and utilizing the density matrix renormalization group, DMRG, simulations. The Hamiltonian of the system is expressed in terms of spin operators for spin 1/2 and spinoni states, along with the interlayer repulsive density interaction. Model parameters, such as JS's, JSD, JDD, T-parallel, and T-uptack, are derived from microscopic parameters, with relationships JS's equals C, R, JSD equals C, R, 2 JDD uptack, JS's equals C, R, AJSD equals C, R, 2A 2 JDD parallel, and A approximately equals 0.7705. Using DMRG simulations, the spin gap in the system is calculated, indicating the emergence of the Luther-Emery liquid phase with power law interlayer pairing correlations. The pairing gap decreases with increasing T-uptack but remains robust at small values of T-uptack. The doping dependence of the pairing gap is also explored, showing a dome centered near x equals 0.40.5 in the presence of a finite interlayer repulsive interaction. This suggests that the bilayer type IITJ model could be relevant for understanding high-temperature superconductivity observed in bilayer nicolates. In the context of bilayer nicolates, LA3 Ni207, a theoretical study reveals the crucial role of the Zhang-Rice spin-half state as the dominant hole state. The Type 2 TJ model emerges as a minimal model for both bilayer and trilayer nicolates, distinct from holodopped cuprates due to strong interlayer spin-spin coupling. This leads to an optimal doping of 4050% in the bilayer Type 2 TJ model, contrasting with 20% in cuprates. Density matrix renormalization group, DMRG, simulations are employed to investigate the doping and pressure dependencies of the spin gap, delta S. The results show a monotonic decrease in the spin gap with increasing T-uptack in the large J-uptack limit. Furthermore, the paper explores the superconducting dome and its relationship with pressure. Increasing pressure is expected to enhance TdP, Z and thus the J-uptack term, initially leading to an increase in Tc. However, when pressure exceeds an optimal value P, the hole prefers to stay in the PZ orbital, resulting in the suppression of pairing and a decrease in Tc. The analysis is generalized to trilayer nicolates, La4 Ni3010, with the proposal of a trilayer version of the Type 2 TJ model as the minimal model. Here, both D1 and D2 orbitals are assumed to be at fractional filling, with mobile carriers from both orbitals. In contrast, in the charge transfer picture, both D1 and D2 are localized, providing a spinoni moment at each Ni site. The final model is one orbital-like, similar to the bilayer case. The paper highlights the significance of the Zhang-Rice spin-half state in the Type 2 TJ model in understanding the physics of bilayer nicolates. Future studies will focus on the analysis of the trilayer model. Recent studies on bilayer and trilayer nicolates have shed light on the crucial role of interlayer coupling in the emergence of superconductivity. Understanding the relationship between interlayer coupling and superconductivity is essential, yet challenging, due to the complexities involved. A comprehensive review of previous studies highlights the significance of interlayer coupling as a driving force for superconductivity, particularly in the context of the Feshbach resonance scenario. Theoretical models, such as the renormalization group method, have been employed to describe the interlayer coupling and its effects on the electronic structure and superconductivity. These models have enabled the calculation of the superconducting transition temperature and the study of phase diagrams in bilayer and trilayer nicolates. Experimental techniques, including angle-resolved photoemission spectroscopy, ARPES, and scanning tunneling microscopy, STM, have been used to measure the interlayer coupling and its correlation with superconductivity. These experiments have revealed the complex interplay between interlayer coupling, electronic correlations, and superconductivity in bilayer and trilayer nicolates. The findings of these studies have significant implications for our understanding of superconductivity in these systems. However, further theoretical and experimental investigations are necessary to fully elucidate the mechanisms underlying the emergence of superconductivity. The development of high-temperature superconductors relies on a deeper understanding of the interplay between interlayer coupling and superconductivity in bilayer and trilayer nicolates. The research on superconductivity in bilayer nicolate La3Ni207 and trilayer multiorbital models of La4Ni3010 is a significant area of study in the field of condensed matter physics. A seminal work by Zhang and Visvanathan, 58, explores the intricate relationship between physical phenomena and their theoretical explanations, providing a foundation for understanding the complex interplay of factors that contribute to superconductivity in these materials. In the context of bilayer nicolate La3Ni207, the study of superconductivity is particularly intriguing due to its potential implications for high-temperature superconductors. These materials have the ability to conduct electricity without resistance at temperatures above the boiling point of liquid nitrogen, which could revolutionize a wide range of technologies. The bilayer structure of La3Ni207, consisting of alternating layers of Lao and NiO2, creates a unique electronic environment that fosters the emergence of unconventional superconductivity. The trilayer multiorbital models of La4Ni3010, on the other hand, offer an opportunity to explore the role of orbital degrees of freedom in the development of superconductivity. The trilayer structure consists of 3 layers of NiO2 separated by 2 layers of Lao, resulting in a more complex electronic structure compared to the bilayer model. This complexity can lead to novel superconducting states, such as unconventional pairing mechanisms and non-trivial topological properties. Both the bilayer and trilayer models have been studied using various theoretical approaches, including density functional theory, DFT, and dynamical mean-field theory, DMFT. These methods allow researchers to simulate the electronic structure and predict the emergence of superconductivity in these materials. The results of these studies suggest that the nicolate family may exhibit a variety of superconducting states, including S-wave, D-wave, and even topological superconductivity. However, despite the promising theoretical predictions, experimental evidence for superconductivity in nicolates remains elusive. This discrepancy between theory and experiment has sparked intense debate within the scientific community, with some researchers suggesting that the lack of superconductivity may be due to the presence of impurities or defects in the material. In conclusion, the study of superconductivity in bilayer nicolate La3Ni207 and trilayer multiorbital models of La4Ni3010 is an active area of research in condensed matter physics. Theoretical models predict the emergence of unconventional superconductivity in these materials, but experimental evidence remains lacking. Further studies are needed to understand the underlying mechanisms and to identify potential pathways for achieving high-temperature superconductivity in nicolates. The supplemental material for the paper, Type 2 TJ model in charge transfer regime in bilayer La3Ni207 and trilayer La4Ni3010, delves into the symmetry properties of the charge transfer Hamiltonian. The Hamiltonian exhibits D4H point group symmetry, a direct product of D4 and I. Notably, the two orbitals are unidimensional irreducible representations of D4H, whereas the orbitals do not share this property. To classify the orbitals as a symmetry representation, the symmetry actions of these orbitals are identified under the D4 group operations, including C4, C2, C2, and C2 rotations. By solving the eigenvalues of these symmetry actions, it is found that the linear combinations of orbitals, denoted as P1 and P2, become unidimensional representations with B1G and A1G representations, respectively. This classification is verified by the character table in Table S1, which tabulates the characters of each orbital and the irreducible representation. The notation G, U, is used to denote even, odd, symmetry under the inversion I. The symmetry properties of the charge transfer Hamiltonian are crucial in understanding the behavior of the system. The identification of the orbitals as unidimensional representations with B1G and A1G representations provides valuable insights into the electronic structure of the bilayer La3Ni207 and trilayer La4Ni3010. These findings have significant implications for the development of the Type II TJ model in the charge transfer regime. The nearest neighbor hopping terms between orbitals are represented by the Hamiltonian HDP, which consists of two components. The first term represents the hopping between nickel and oxygen atoms, while the second term represents the hopping between oxygen atoms. The phase factors T1, I, alpha, I, and T2, I, alpha, I, are defined accordingly for each hopping term. By substituting these expressions into HDP, the Hamiltonian simplifies to a form introduced in the main text. The irreducible representation and character table of the D4H point group are presented in Table S1, listing the orbitals Re2C4, Z, C22C, 22C, 2I, D1, L, P1, L, B1 gram, D2, L, P2, L, A1 gram, and D2, TD2, B, PZ, A1U. The paper then analyzes the energy of possible D8L states with general values of Jk and Jh in the strong coupling limit. The local Hamiltonian is defined at each site, neglecting the hopping term, and is expressed as a function of Jk, A, Jk, Z, and Jh. The analysis reveals three possible states depending on the orbital occupancy: Np, L, 1 equals 1, Np, L, 2 equals 1, and Np, L, Z equals 1. For the cases where Np, L, 1 equals 1 or Np, L, 2 equals 1, the local Hamiltonian reduces to a three-site Hamiltonian, which is solved to obtain the ground state wave functions, L and L, corresponding to the Zhang-Rice spin-half state. These wave functions are entangled by the three P1, D1, D2 orbitals and are illustrated schematically in Fig. S1. The parameters r and alpha, r, are defined in terms of Jk, A and Jh, and the wave functions are expressed in terms of these parameters. The derivation of the type IITJ model from the charge transfer Hamiltonian is a pivotal step in understanding the spin exchange interactions between two nickel atoms. This process involves dividing the charge transfer Hamiltonian into a kinetic part, V equals HDP, and a remaining part, H0 equals HV. The J-up tack terms are then derived, with the example of J-up tack SD being demonstrated. Due to the SU symmetry of the Hamiltonian, generalization to J-up tack SS and J-up tack DD is straightforward. There are 6 different processes contributing to the STS plus B term, as illustrated in Figure S3, These processes, denoted as A through F, are summed up in equation S8. This equation highlights the complex interplay between various components of the Hamiltonian and demonstrates the importance of considering higher-order perturbation terms in the strong coupling limit. The paper also discusses the Zhang-Rice spin 1/2 and spin 3/2 states of D8 electron configurations in bilayer nickelates, shown in Figure S1. The spin 1/2 state, particularly with a P1 hole, is found to be the most stable state, as evidenced by the energy comparison in Figure S2. In conclusion, this section provides a detailed explanation of the derivation of the type IITJ model from the charge transfer Hamiltonian, emphasizing the role of spin exchange interactions and the stability of the Zhang-Rice spin 1/2 state in bilayer nickelates. The effective Hamiltonian, H, for the Zhang-Rice spin 1/2 state in a two-band Hubbard model with finite Hund's coupling is calculated using the Schrieffer-Wolff transformation. This transformation eliminates doubly occupied states and projects onto the subspace of all excited states, enabling the evaluation of matrix elements between different states, denoted by A and B. These components are crucial for understanding the stability and properties of the Zhang-Rice spin 1/2 state. Component A is calculated as a function of parameters TdP, Z, increment Z, P, JH, U, and alpha, involving the projection of the transformed Hamiltonian onto states SD1 equals 1/2, SC equals 1/2, and SD1 equals 1/2, SC equals 1/2, with an additional hole in the pz orbital. This component reflects the energy gain from the formation of the spin 1/2 state and is significant for its stability. Component B is derived using the Schrieffer-Wolff transformation and involves the projection onto state SD1 equals 1/2, essential for understanding the role of Hund's coupling in the two-band Hubbard model and its influence on the stability of the Zhang-Rice spin 1/2 state. The bipartite entanglement entropy, S, is calculated as a function of distance, r, representing the degree of quantum entanglement between the d1 and p1 orbitals. As r approaches infinity, the entanglement entropy approaches zero, indicating that the Zhang-Rice spin 1/2 state becomes a tensor product of the singlet formed by the d1, p1, and spin 1/2 of the d2 orbital. These calculations provide a detailed analysis of the effective Hamiltonian components and bipartite entanglement entropy for the Zhang-Rice spin 1/2 state, vital for understanding its stability and properties in the context of high-temperature superconductors. The spin exchange interaction terms J_SD, J_DD, and J_SS are derived through fourth-order perturbation processes, as depicted in Figure S3a. These expressions are obtained in terms of C, R, TdP, Z, increment ZP, 2, JH, and U2, where C, R, is defined as 4, 1 plus R plus alpha, N2 with alpha equals square root, R2 plus R plus 1, and N equals P2, R plus alpha, 2 plus R plus alpha plus 1. The R dependence of C, R, is illustrated in Figure S3b, which approaches 4/3 in the R right pointing arrow zero limit. The derivation of J parallel terms is also outlined, highlighting two key differences compared to J_TAC. Firstly, there are two types of hopping processes, involving TdP, 1 and TdP, 2. Secondly, the p orbital of the Zhang-Rice spin-half state can be affected by the hoppings, as the intermediate occupied oxygen is shared by those states. An example of the hopping process px I plus bx2 sigma is used to illustrate how the p orbital is affected, leading to a modified expression for phi I, sigma. In a two-dimensional, doped Mott insulator, the spin gap is analyzed using quantum fidelity, which measures the overlap between two quantum states. Fidelity, defined as f equals less than phi, greater than, quantifies the similarity between the states. The authors derive equations for the in-plane hopping term, T parallel, I, J, with and without spin dependence, which they classify into effective O-hopping and spin exchange between Ni and O holes, analogous to cuprates. Additional DMRG simulation results are presented, including the T-parallel dependence with varying interlayer repulsive interaction strengths V. These results demonstrate how the non-monotonic decreasing region diminishes and eventually disappears as V increases. The authors also provide DMRG simulation data at x equals 0.2, which exhibits similar key characteristic behaviors to the data at x equals 0.5 presented in the main text. A convergence check is performed under different system sizes, verifying the spin AP results through DMRG calculations. The derived equations and simulation results in this section are crucial for understanding the spin gap in the system, with implications for the study of quantum phase transitions and superconductivity in doped Mott insulators. The supplementary figures S4, S5, and S6 in the research paper provide additional insights from the density matrix renormalization group, DMRG, simulations of the type IITJ model. Figure S4 illustrates the dependencies of the transverse hopping integral T parallel and the density of states n, r, on the model parameters, as estimated in the main text. The spin gap delta S is represented in units of eV, while n is a dimensionless quantity. Figure S5 presents the DMRG simulation results for the type IITJ model with Ls equals 2, Li equals 1, T parallel equals 1, and J's parallel equals 0.1. The spin gap delta S is shown as a function of the transverse hopping integral T up tac for various values of the Coulomb repulsion V, at doping levels x equals 0.5 and x equals 0.2. A non-monotonic decrease of the spin gap with increasing V is observed, indicating the transition to the Bardeen-Cooper-Schrieffer (BCS) limit. Figure S6 shows the DMRG simulation results for the type IITJ model at x equals 0.2, with Ls equals 2, Li equals 1, T parallel equals 1, and J's parallel equals 0.1. The pair correlation function and entanglement entropy are calculated for various values of J up tac and T up tac. The results exhibit evidence of the Luther-Emery liquid phase, characterized by power law decaying behavior of the pair correlation function and a central charge C approximately equals 1. The entanglement entropy and correlation length are also shown to exhibit the expected behavior in this phase. These supplementary figures further support the emergence of the Luther-Emery liquid phase in the type IITJ model, and demonstrate the robustness of the results presented in the main text. The authors present supplementary analysis on the pressure dependence of critical temperature in the type IITJ model, focusing on the system size dependence of DMRG simulation results. Figure S7 showcases the spin gap's dependence on transverse exchange coupling J up tac and doping X, highlighting the interplay between these parameters. Figure S8 examines the TdP, Z dependence of the binding energy per unit cell, a crucial factor in estimating the critical temperature under pressure. The results reveal a transition from P1 dominance to PZ dominance at TdP. Z approximately equals 2.50 electron volts. In the P1 dominant regime, the binding energy increases with pressure, suggesting a rise in Tc. Conversely, in the PZ dominant regime, the binding energy decreases under pressure, implying a decline in Tc. The binding energy is analyzed in two distinct regimes: P less than P asterisk operator and P greater than P asterisk operator. For P less than P asterisk operator, additional holes occupy the P1 orbital, while for P greater than P asterisk operator, the PZ orbital becomes dominant. The binding energy is estimated using equations E1b and EZb, respectively, for each regime. Figure S8b illustrates the pressure dependence of the binding energy per unit cell, demonstrating a positive trend in the P1 dominant regime and a negative trend in the PZ dominant regime. In the charge transfer regime, trilayer nicolates La4Ni 3010 exhibit a theoretical framework that is crucial for understanding their behavior. The valence of the Ni atom in La4Ni 3010 is found to be in a 3D 7.33 configuration, with the dx2-y2 orbital nearly one-third occupied and the dz2 orbital almost half-filled. This configuration plays a pivotal role in the behavior of these materials. The lattice structure and orbital configurations of La4Ni 3010 are also discussed, highlighting the presence of two d orbitals at each Ni atom and p orbitals at each O atom. The oxygen atoms residing between layers have pz orbitals shared by two adjacent Ni atoms, leading to a local trilayer version of the charge transfer Hamiltonian. This trilayer model can be generalized from the bilayer model. The Kondo Hamiltonian derived from this trilayer model includes terms related to the interaction between spin and pseudospin operators, as well as the number of holes in different orbitals. There are three possible one-hole states depending on the occupancy of p orbitals. NPL 1 equals 1, NPL 2 equals 1, and NPL Z equals 1. The local Hamiltonian for the first two cases results in a ground state energy of Eg equals minus 2 plus R plus PR2 plus R plus 1, JH, where R equals JK. JH is a dimensionless parameter. For the last case, the local Hamiltonian is different, leading to a distinct ground state energy expression. The author's work aims to provide a comprehensive understanding of the electronic structure and magnetic properties of trilayer nicolates, which are essential for the development of new materials with potential applications in various fields. The ground state energy of the Zhang-Rice spin 1/2 state is calculated as equation S18, involving a dimensionless parameter r, which equals jk z divided by jh. This result is a constant shift from equations S6 S7, leading to the same conclusion. Assuming TdP 1 is approximately equal to TdP z and greater than TdP 2 and increment p 1 is approximately equal to increment z, increment p 2 is approximately equal to increment p 2, we get jk 1 is approximately 4 times jk z greater than jk 2. This leads to the relation E1 underscore g, jk 1 is less than E2 underscore g, jk 2, and E1 underscore g, jk 1 is less than Ez underscore g, jk z approximately equal to 4 times jk 1. Therefore, we can conclude that the Zhang-Rice spin 1/2 state, especially with P1 hole, is the most stable state even for the trilayer nicolates. The trilayer nicolates can be modeled using the type IITJ model, where the Zhang-Rice spin half is the primary state of the D8L state, and the spin triplet Dublin state of the D8 state is kept. The Hamiltonian for this model is given by equation S19, which consists of several terms: the kinetic energy term Hk, the spin-spin interaction term with coefficients J parallel and J uptack, and the Coulomb interaction term. The coefficients J parallel and J uptack are listed in equations S9 S14. The Hamiltonian Hk is further divided into two parts: the inplane hopping term and the interplane hopping term.